good morning everybody, and thank you very much to the organisers for the opportunity to come and talk today. So I'm based in the School of Physics. You can see that I've already forgotten to include our full new title, but also one of the research centres, the DIT Centre for Radiation and Environmental Science. So as Siobhan said, I'm going to be talking about biophotonics. So biophotonics is, as we said, does it work? Multidisciplinary research area that uses light. So light-based technologies in medicine and the life sciences. And you can see that biophotonics even got a shout out on the Big Bang Theory. So even people at Caltech are doing biophotonics as well. So one of the main technologies in biophotonics is vibrational spectroscopy. So I'm just going to give you a very sort of quick overview. So spectroscopy is really just the interaction of light with matter, and vibrational spectroscopy then analyzes vibrations within a molecule. And the spectrum of vibrational energies can be used to characterize a molecular structure or changes to that structure. So if we shine light on something, if we shine light on anything at all, that light can be reflected, it can be transmitted, or it can be scattered. And this is what I'm going to be talking about, the scattered light. So most of the light that's scattered will have the same energy or frequency as the incident light. And as you probably know, this is called Rayleigh scatter. So this is elastic scattering. But a small amount of the light can be inelastically scattered, and energy can be transferred between the light and the molecules of the scattering medium. And this is what Raman scatter is all about. So just to go into it in a little bit more detail, as we said, when we shine light on something, so here's the incident light, the molecule can move from the ground state to a virtual state, and then we can get emission of light. And when it goes back to the ground state, that light can have the same energy or frequency as the incident light. So again, this is just Rayleigh scatter or elastic scatter. Then we can have the inelastic scattering, which we can have Stokes or anti-Stokes. So the molecule, again, is in the ground state, goes to the virtual state, and it falls back down, but to a different energy state, an excited state. So we have an energy difference then. So when we have this situation here, the Stokes situation, we have basically less energy than the incident light. So this is called Stokes-Raman scatter. We can also have a situation where the molecule starts off in a higher energy state and then it falls back down to the ground state with the emission of a photon. And here the photon will have higher energy, so a bit more energy. Now mainly molecules at room temperature are already in the ground state, so mostly what we measure in Raman spectroscopy is Stokes Raman scatter. Okay, so who discovered all of this? This was an Indian physicist called C.V. Raman, so it was named after him. And he got the Nobel Prize in Physics in 1930, so he discovered it in 1928. So this is C.V. Raman, and I really like this little cartoon. This is of his original experiment. So he used light from the sun, brought through a telescope. He shone it onto this CHCl4, and he observed light of a different colour. So that's all it was, light of a different colour. So the different energy because of the interaction of the incident light with the molecules, and that gave light of a different colour. So the difference in energy then between the incident photon and the Raman scattered photon is equal to the energy of vibration of the scattering molecule. So then a plot of the intensity of the scattered light versus the energy difference is the Raman spectrum. So here's a very simple sort of look at what a Raman spectrometer looks like, very sort of schematic. It can be used in sort of different modes. You can even get Raman spectrometers now that would be handheld, you know, quite small instruments. I'm showing here just something through a microscope so you can see an objective lens. So basically the laser light comes through the objective lens. This green light, you can't really see it unfortunately, shines onto the sample. Then we have the scattered light. This is collected through the objective lens. We have both elastic scatter and then the inelastic Raman scatter. We have a notch filter here which rejects that elastically scattered light. So light of the same energy is rejected and isn't collected into the rest of the optics. So only the inelastically scattered light, the light of the different energy or the different color, comes through, hits the grating, and then it's dispersed onto a CCD detector. And then the output is something like this, so a spectrum. This is what we're measuring. So this is, these are pictures of actual Raman instruments that we have in the Focus Institute in DIT in Kevin Street. This is one of the high resolution Raman systems, and you can see it's a fairly big system. It's got 2 microscopes, it's got a couple of lasers back here, and all the optics kind of at the back there. So this will be the typical sort of system that people would use for material science, physics, chemistry. And then in the lab also we have a couple of smaller systems, which is basically just a microscope with this box on top, which is where the spectrometer is. So this is a, let's say, more user-friendly, more simple kind of system that we're using for our biophotonics applications. So some examples then of Raman spectroscopy, some applications where it's used. So it's used quite a lot in the pharmaceutical industry, and you can see here, this is an aspirin tablet. This is a Raman map of an aspirin tablet showing the different molecular composition, so the different ingredients that would be in a tablet. And you can see here that each of those ingredients has its own unique Raman fingerprint. It's also used in art and archaeology, in forensics, looking at blood or hair, different materials and even nanomaterials. In geology, you can see here olivine, the Raman spectrum of this particular sort of geological sample. It's also used in food science, so it's used in a huge amount of different applications. So I'm going to be talking about its use in biomedical applications. So the Raman spectra of cells and tissues are really just a superposition of all of the contributions from each of the different biochemical components of cells. And you can see a Raman spectrum here of a cell, this black spectrum at the top. And if you look at the other spectra underneath, we've got DNA, we've got RNA, we've got phospholipids, and we've got proteins. These are all different molecular composition of cells and tissues. And you can see that the spectrum at the top, the black one, is made up of contributions. So you can see a lot of the bands that we have here are basically, it's an overall spectrum is what we measure in the cell or tissue of each of those components. So Raman spectroscopy then can provide a molecular diagnosis by providing a biochemical fingerprint of a cell or tissue. So this is what we're using it for. We're using it to molecularly fingerprint cells and tissues. So I'm going to tell you a bit about the two different applications that we're using it for. The first is cervical cancer. So cervical cancer is the 4th most common cancer worldwide for females. But the good news about cervical cancer is it's 100% treatable, but only if it's detected early. So it must be found early for it to be treated. So this is why screening programs are commonplace in most developed countries. So the PAP test is the test that's used in most cervical screening programs, and it's used here in Ireland, Cervical Check. So what happens is cervical cells are scraped from the cervix using a brush like this. The cells are then placed into a vial of liquid preservative, and then that's sent off to the lab. And those cells are then placed on a slide like this one here. And then the cells are stained with a couple of different dyes called a PAP stain. And then this is what the cells look like at the end. So this is all very well, and this technique, the PAP test, has been used since the 1940s. And of course, it has reduced mortality due to cervical cancer. But there are, of course, problems with it. So although it has a high specificity, it's well known that, the sensitivity is low, so it has a low sensitivity. The test itself is very subjective, so it's based on a cytologist looking down the microscope at the cells and judging whether the cells are a little bit different looking than normal cells, so it's quite subjective. And this can lead to inter-observer variation. So I might say, I think that cell looks a little bit different. You might say, no, I think it looks fine. So this is why there are false positives and false negatives with this test. Another issue is that precancer can be difficult to distinguish from benign conditions. So normal things like inflammation in cells can look like cancer when you're looking at it under the microscope. The other problem is that all cytology has to be confirmed with biopsy and histopathology. So a piece of tissue must be taken from the cervix and then again put into wax, make sections and look under the microscope again by a pathologist. But again, this also suffers from the exact same limitations in terms of sensitivity and subjectivity. So what's the clinical need here then? So there's an unmet clinical need for new methods to aid cytologists in the early detection of cervical precancer. So ideally these methods should be rapid, objective, non-destructive and require minimal sample preparation. I thought I had another slide there in between. So we think that Raman spectroscopy fits the bill here. We think that Raman spectroscopy, in its ability to molecularly fingerprint a sample, could be used in cervical cancer. So this is what our workflow looks like. The sample is collected from the cervix, sent to the laboratory, the slide is made, routine cytology is performed. Once that case is reported, we then have ethical approval to get access to the same vial of cells. We can take some of the cells, make an additional slide. We can't use the stain slide because unfortunately the stains themselves have their own unique Raman fingerprint as well. So we must use unstained material. We do a pre-treatment to get rid of any blood and contaminating material. We do our Raman spectroscopy, our data analysis, and then at that point we can add the stain and have a look at the cells. So this is what the cells look like then unstained. You can see them here, and this is what they look after staining. So it's not so bad. You can find the cells, you can find this black circle in the center is the nucleus, and this is where we're targeting. The nucleus is where all the DNA and RNA is, and this is usually what's different between normal cells and abnormal cells. So you can see that there are mainly 3 different types of epithelial cells on the slide. There are these small blue ones here. I don't know how good you can see them, but these are immature epithelial cells called basal or parabasal cells. Then we have these bigger blue ones, they're called intermediate cells. And then these pink ones are called superficial cells. And these are just from different layers of the cervical epithelium. And each of these different types of cells has its own unique Raman fingerprint. Here's the Raman spectra here. And you can see that those parabasal, those small cells, when we use a data analysis method, an unsupervised method called principal component analysis, where basically all we're looking for is differences between the spectra. So we're looking for what's different between each of these spectra. So the parabasal cells, we can see that we can separate those from both the intermediate and superficial cells, and also we can separate the intermediate cells from the superficial cells. So we can tell the difference just from the spectrum, okay? And those differences you can see in what are called loadings plots, and they're just simply the biochemical differences. So they're generally, the parabasal cells are different in that they have more nucleic acids because they're proliferating more, they're replicating more. And then the intermediate and superficial cells generally have differences in proteins and lipids. So when we look then at the differences between normal cells and different grades of precancer, so this is called CIN, or cervical interepithelial neoplasia. So we have different grades. CIN 1 would be termed low grade, and CIN 2 and 3 would be termed high grade. So the Raman spectra are shown here. This is from a study that we've done of about 300 patient samples. So we have normal cells here in green, the low grade in pink, and then the red and the black are the high grade. And again, using the principal component analysis that I mentioned, which is an unsupervised method, we can see that we can basically cluster together the spectra from the normal cells, the spectra from the low-grade cells, and the spectra from the high-grade cells. So we can basically tell from that molecular fingerprint whether it's normal, low-grade, or high-grade. And again, these are the loading plots telling us the differences, and again, the differences are mainly due to nucleic acids, proteins, and lipids. We can also do something called a supervised analysis, so principal component analysis, linear discriminant analysis, and this allows us basically to build a classification model. So using basically a modeling set of data where we know that it's negative or low grade or high grade, and then we use a test set where we don't know what it is and we try and classify which grade of cancer or whether it's normal. And you can see that we can do this with very high sensitivity and specificity, so between 90 and 100%. So this is much better than what's currently used in the PAP test. So in this application on cervical cancer, our ongoing work then is we're carrying out a clinical utility study of Raman spectroscopy on 1,000 patients who are attending a colposcopy clinic at the Coombe Women and Infants University Hospital. And this is work that's funded by the Health Research Board. So we're about a third of the way through that study at the moment. So hopefully we'll be able to report on it sometime next year. So just one further example I'm going to show you, and it's on oral cancer. So oral cancer, it's the 6th most common cancer worldwide. The 5-year survival rate is about 80% for early stage disease, but it's only 20% for late stage disease. So you can see that it's really important again to catch this one early. Another issue with oral cancer is that multiple primary tumours are common. So when the dentist finds something in your mouth and sends you to the dental hospital, often they can find several lesions in the mouth. So it's very difficult for the clinician to know which one is the one that's going to become a cancer, because they all potentially could. And again, it's very difficult for them to biopsy several areas in your mouth. So again, like with cervical cancer, there's a need here for an objective technique. So what's done at the moment is they take a biopsy, they do the histopathology. But again, as I said, this has limitations. So we feel that Raman spectroscopy could have a role here. Not here in Ireland, but in some countries they do what's called a brush biopsy. So instead of taking an actual scalpel biopsy of a piece of tissue from the mouth, they take a brush and they rub it over the lesion, and they collect cells into the vial, very similar to what's done in cervical cancer. So you can get then, and again they use the same pap stain, so you can get a pap stain of the cells from the lesion. So again, you can see the same type of cells we looked at before, the basal cells, the intermediate cells, the superficial cells. So we're trying to apply this same cytology approach for Raman spectroscopy. So again, our workflow, at the moment we're doing a healthy volunteer study. We're just getting these methods established before we move to patient samples. So at the moment we're collecting samples from 2 areas of the mouth, the buccal mucosa, which is just the inside of the cheek, and then the ventral side of the tongue, so just underneath the tongue. So we collect the cells into the vial, we make the slide, we put it under the Raman, we do our analysis, and we do our pap stain. So these are what the spectra look like. So here, as well as recording spectra from the nucleus, which is where all the DNA is, we're also looking at the cytoplasm. This is where most of the protein would be. So we can see when we do our unsupervised principal component analysis, we can separate out the data based on whether it's recorded from the nucleus or from the cytoplasm. So you can see in black and in blue nuclear spectra from both the tongue and the buccal mucosa, and in pink and red protein spectra from the buccal mucosa and the tongue. And the loadings plot then tells us that what's different is in the nuclear spectra we have nucleic acid peaks, which are the ones circled in blue, and in the cytoplasm spectra we have protein peaks, which are the ones in green. So this work is still at an early stage. It's funded by Science Foundation Ireland, so we're just getting the methods up and going. It seems to be working. We're able to record spectra. We can see differences between different subcellular regions, and we're going to continue to collect about 100 samples from healthy volunteers, and then we've got ethical approval to go to the dysplasia clinic at the Dublin Dental Hospital, and we're going to collect samples from patients there who are showing lesions in their mouth, and we're going to try and do what we did with the cervical cancer and see can we grade them, or can we predict which ones might need to be further looked at. We also have approval to follow the patients. So often with lesions of the mouth, patients go into the dysplasia clinic and they're followed up. So nothing might be done. They might just say, come back and we'll have a look. So we'll have access to all of those medical records as well. So it means that something that we can see using Raman spectroscopy, we can relate then to the clinical outcome of these patients. So I'm going to finish there and just thank all of my colleagues at the Dublin Institute of Technology, in particular the students, Damien, Inesh, Isha and Ola, postgraduate students who would have done all of the work that I've shown here. And our clinical collaborators from the Coombe Women and Infants University Hospital, Altona-Gelvin Hospital in Derry and the Dublin Dental Hospital. And then of course our funders, because without them we wouldn't be able to do this work. And thank you for your attention.